Hello everyone. So today I'm going to solve a previous year's question, that is 2022 term 2 theory paper CBSE physics. Let's see what are the questions there. So here is the paper, theory paper. So without any delay, let's start. So actually in 2022 there are two terms, term 1 and term 2. Term 1 was completely MCQ and term 2 was theory. So in this paper you will see only descriptive section is there, and MCQ portion was taken in the term 1. So there are one case study in this year. There were two case study based questions, but in 2022 there are only one case study question, as you can see. So let's solve all the question. See, I'll try to share as much technique as possible to solve these questions. So the first question is, draw the energy band diagram of N-type and P-type semiconductors at temperatures T greater than 0. So as you know, so let us revise also. So what is the semiconductors? If you know, semiconductors are the devices. So semiconductors are the devices, are the elements which are perfect insulators or resistors, perfect insulators or resistors at 0 Kelvin. At 0 Kelvin, but as the temperature increases, they become very good conductor. So they can be semiconductors can be of two type. What are they? They can be P type and they can be N type. N type. Now how do you create P type? P type, we create a P type by adding what? By adding trivalent impurities. Trivalent impurities. You may no need to know the element and all. Many people tends to forget. Just remember the valency is +3. They are called trivalent impurity. And N-type semiconductors are what? They are produced by adding pentavalent impurities. Pentavalent impurities. That is +5. So when you do this, what happened? In terms of energy band diagram, we can explain them that in case of metals, you will see there are some called energy bands. Energy bands continuous energy levels which electrons occupy. Okay, continuous energy levels. So in case of metals, either they're separated by very small distance, or sometimes they overlap. This is the case of metals. So this is the C overlap. So metals conduction. This top band is called the conduction band, and the below one is called the valence band. Conduction band and valence band, they overlap. So this is the case of metal. But in case of um, insulators, this gap is very large, very large, very high. It is not possible greater than 3 electron volt. It is not possible for any electron which is present in the valence band to jump and go there, get enough energy from the surrounding and jump and go there to the conduction band. It is not possible for any electrons to gain this. So they are perfectly insulated for this. Now come to semiconductors. For semiconductors, this gap is not very much. The energy is quite electrons can achieve this energy from the surrounding, and then they can jump to the from valence band to conduction band. They can easily jump. So this is the case of the semiconductor. This gap, energy gap is quite less, so they can easily get it and jump this. So by the way, this is called the conduction band, this is valence band. Now in case of p-type and n-type semiconductor, this thing, when we add trivalent impurity, what will happen? These electrons energy will not be same as the energy of the semiconductor. So in that case, the energy diagram, energy level diagram for semiconductors will be, for a p-type semiconductor will be, there will be some holes present here, some few electrons, and there will be one level just above this. This level is called the acceptor level. I'll write it in some other color, called the acceptor level. ACPTOR, acceptor level. They just have an electron can easily jump from this one and go to the acceptor, and they can participate in the conductivity. So this is the diagram which you need to draw in this case, that energy band diagram for n-type and p-type. So this is the n-type done, p-type done. Now let us do for the p-type, sorry, n-type. So for n-type, again there will be conduction band, and there is a valence band. Clear? Conduction band and valence band. Now in this case, the electrons, the trivalent impurity electrons will have, you know what, the conduction band is completely empty. One or two electrons may be present there. The conduction band, in case of n-type, there will be many electrons there at the conduction band. Now the impurities that you add, their energy is little less than the energy of the electrons of the semiconductor, like silicon, germanium. So they take a level just below the conduction band. This level is called we call it donor level. This level we call it donor level. So this is what you just need to draw. In this case, I just gave you a revision on this, but the answer to this question would be just to draw these two pictures, and that's it. That would be your answer for this case. That means you need to draw this one and this one. That's it. You just need to draw these two, and that would be your answer. 2 marks done. I just gave you the revision so that you know what to do or what not to do. Okay, so I will clean this. These are just for your revision purpose. So the answer is this one. So 2 marks done. Here are the bands. Okay, so there will be field electrons in here. This is valence band, this is conduction band. That's it. So this is for 2 marks. So 2 marks done. That's much. This is just for revision purpose. You do this, finish. Next, let us come to the next one. Question number 2. That is, draw the graph showing the variation of number of scattered alpha particles with scattered angle theta in Giger-Marsden experiment. So what is Giger-Marsden experiment? Giger-Marsden experiment, if you remember, it is the most common name is the alpha particle scattering experiment. If you remember alpha particle scattering experiment, there is a gold foil like this, and there are then detectors like this. There are photographic plates which are used as detectors like this. So the purpose of this detector is this and what happened? An alpha particle is a highly accelerated alpha particle from a radioactive source is allowed to pass through the gold nucleus. Before this, the model of atom was Thomson's model, which is incorrect. Now there comes the Ernest Rutherford. So who, along with his student, carried out this experiment. What is he allowed an alpha particle from radioactive source to pass through the nucleus of gold nucleus, and what he observed? He observed that his observations were that most, remember this observation you infer two conclusion from the graph. So most, what he observed, most of the alpha particle passes through it directly, and they create a small dots on these photographic plates. Few few of them get scattered here at a small angle, few of this, and extremely few of them will return back. So when he plotted how many number of alpha particles just getting scattered, he got a graph something like this. He got a graph similar to this one. This is the graph. You need to draw this. This is the number of particles scattered, and this is the scattering angle theta. What do you note? For small scattering angle, number of particles scattered is more. That means most of them. This comes to most of them. First conclusion, what you can draw from the graph directly, then most of the alpha particles passes through. Most of the alpha particles, conclusion, what you can draw, most of the alpha particles passes through the gold foil. First thing, that is what he has observed. Then if you see, only few particles, there are only few particles, look at this portion of the graph, only few particles are scattered at, only few particles would be here, and look at this one here. You can see only few particles is scattered at large angle theta. Only few particles get deflected by more than 90 degree, okay, 90 degree or more. Only few, you can see theta here is more, number of particles is less, and there are only extremely few alpha particles, very few particles, very 1 in 8,000, 1 in 8, that is around 1 in 8,000 alpha particle get deflected by 180 degree, means it returns its path backward. Get deflected by 180 degree, that is retraces path backward. These are the few. This is what this question has asked you. I have given you 3 references here, 3 observations. That's it. So this is again for 2 marks. So how will it be marked? It will be marked here 1 mark. This one definitely will be 1 mark, and this one would be half plus half mark, like this. They'll give you 2 marks. Now let us see the third question. Odd question. Let us do the odd question. So for the odd question, let's see. So plot suitable graph to show the variation of photoelectric current with the collector plate potential for the incident radiation. Again, before we proceed, let us revise it. If you remember, photoelectric effect is the phenomenon of producing ejecting electrons from metal surface by inciding the light of suitable wavelength on a photosensitive material, and consequently the electrons are ejected from the metal surface and you get a current called photocurrent. So this effect, so how do we first say the Leonard experiment? The Leonard experiment was something like this. If you remember, revision purpose, I'm revising it also in this case so that we can do. So here was the picture. We had this evacuated glass tube. There is a photosensitive material C, and there is another plate called A. This is called the C is called the emitter plate, and this one is called the collector plate. C is the emitter plate and A is the collector plate. This is the collector plate. This is the emitter plate. Emitter is a photosensitive material. So when light of suitable frequency falls on here, what happens? Electrons get ejected from here. Okay, according to Einstein's relation, part of this incident photon will be used to do work function, and rest of it will be used to increase the impart kinetic energy to these electrons. So when these electrons rushes towards here, under this positive potential, this being the negative potential, this being the positive potential, we get a photocurrent. Sometime what will we do? We will increase this to check how much energetic is the incident electrons are. We will make A, that is the collector plate voltage, negative. So a particular negative voltage at which photoelectrons, these electrons are called photoelectrons. These photoelectrons, which photoelectrons will stop reaching completely, will stop, is called stopping potential. Stopping potential. So now what happened, you see, this is stopping potential thing, which we will see. Now one more thing to note, if the frequency of incident radiation is more, the electrons will be highly energetic. If it is less, below a frequency called nu zero, electrons will not be ejected. That is called threshold frequency. Just a little bit of background. Threshold frequency. So below threshold frequency, no electrons will be ejected. Below threshold frequency. Okay, now what? Now we need to plot. We need to see the intensity of radiation of frequency. This one is nu1, nu2, and nu3. So when light is incident, when light intensity is increasing, means let me use one bulb. Next time I use 2 bulb, 3 bulb, 4 bulb. If you're increasing the intensity, is the electron increasing? Is the photocurrent increasing? Yes. The first graph asks you this. How does it increase? Let's see. You will see that if we plot a graph between photocurrent I, I'll show photocurrent by small, and potential V can be plus or minus. What will you observe? As we increase, keeping the same intensity but different frequencies, if you keep increasing the frequency, what did I say? If frequency increases means electrons become more energetic. So more negative potential you need to stop them. So you can see, so first thing first, with intensity what happened? Current first increases and then it become constant. So now with the frequency, as you increase, what will you see? You'll observe that for this, at this minus negative voltage, minus V1, photocurrent stop. This is the stopping potential for nu1. Similarly, give it another one. This is nu2. It is minus V2. And for the third one, it is more energetic. Nu3 is greater. So here the electrons will be even more. They have many high energy. So they will be stopping here. This is minus V3. So this is the graph they have asked you to draw. Stopping potential for, so this is nu 3, this is nu 2, this is nu 1. Clearly nu 3 is greater than nu 2, greater than nu 1. These are three graphs are present. You should not go without knowing this graph. One questions regarding this will be definitely present. Let us see the second one. The second question it is asking same frequency but different intensities. I'll keep the frequencies to be same. So if the frequency has to be same, and intensity is different. So what did I tell you? With the increase in intensity, what will happen? With the increase in intensity, first current will increase and then it will become constant, saturated. So that is for I1. Similarly for I2, what? First it will increase, then it will become constant. Then for I3, it will increase, constant. Now same frequency means the energy, all of them is same. So they will have only one common potential. That means this one negative potential, same stopping potential. So all of them will come and meet here. Like this. Look how they are decreasing. Little bit of tilted. Okay, like this. So this is how. So this is photocurrent. This is stopping plus positive potential. This is negative potential. This side we call this accelerating potential. This side we call this retarding potential. This is called accelerating potential, and this side positive is called accelerating and negative is called retarding potential. And that particular value, what do you call this? Particular value of retarding potential, where the photocurrent completely cuts off, we call this stopping potential. It is negative. So this is the graph that you want. You don't have to do all this. Just draw this graph. Again, 2 mark will be awarded to you. That's it. Let's proceed to the next question. Now, write the characteristic. The third question says, write the characteristic let us see. Write the characteristic of p-n junction which makes it suitable for rectification. You see, look at a resistor here. If you make this side plus, this side minus, current will conduct. Okay, now you switch the polarity. If you have a resistor again here, this side minus, this side plus, now current will flow this way. But it is not like in case of p-n junction diode. In p-n junction diode, this is, by the way, this is a symbol of diode. This is p side, this is n side. If this side is connected to positive, this side become forward bias, current will conduct now. Current will conduct. But if you connect it in the opposite way, something like this side is negative, this side is positive, then again this is P, this is N, this is called reverse biasing. This is called forward biasing. In forward biasing, diode conduct. In reverse biasing, diode is a perfect resistor. It do not contact these properties. So this one you can see it is bidirectional. But this is unidirectional, only one directional. So this property of diode, the unidirectional property of diode, of p-n junction diode is responsible for rectification. Now, what is rectification? So this one is enough to finish it. You write this much, finish. 2 marks awarded. That's it. It should be done. If you can write this much, it will be awarded. Write the characteristic of p-n junction which makes it suitable for rectification. 2 mark. But then when I am talking about rectification, let us explain you what is rectification. Rectification is the process of what? Converting AC to DC. AC to DC. How do you do it? It can be half wave. It can be half wave. The graph is like this. Half wave, or it can be full wave. So full wave, how is it? Like this. Output voltage like this, again like this. How is the symbol? Just remember, one diode here, another diode here. That's it. And here is the output. This is the resistor, this is the output. I will draw it properly. You can write it like this also, no problem. You don't need to draw transformer also. You can draw this. You can draw one more diode here. And then you can give a resistor here, and you can give an alternating AC source, plus, minus. That's it. This is a full wave rectifier. Here is the output, which is output voltage is like this, like this. Don't go without knowing rectifier. Again, second, for the half wave rectifier, what you can do? Same thing. You will have only one diode here. This is one. That's it. And then from here, we'll have one more, like this. Again, same here. Make is a resistor. This is the output. Only one diode here. This is half wave rectifier. This is half wave rectifier. Only one diode. Here, two diode, D1, D2. This is full wave rectifier. That's it. It conducts, done. Here also you give the input AC wave, plus, minus, and output wave will be like this. Plus, there's a gap, then again plus, like this. This is the output for half wave, full wave rectifier. This much is just the revision on this. And by the way, only this much is the answer you can give, and you will get 2 marks. That's it. As I'm doing revision, so I just gave you the extra work on this one. Now next, let us see the next question. Next question is, define the term distance of closest approach. Let's see, it's a 3 mark. Distance of closest. This here, you can do it, no problem in this. Again, we'll come back to the Giger-Marsden experiment. You can see, so in the Giger-Marsden experiment is alpha particle scattering experiment. So this is our gold nucleus sitting there, and here I'll make it a little bit big, and here is the alpha particle coming from a radioactive source. It is coming along a straight line. You see, this is positively charged, this is negatively charged. This is positively charged, this is also positively charged. The charge on this is Ze. The charge on this is also, this one would be equals to the chemical symbol of alpha particle is chemical symbol is 4He2, like a helium nickel. So this is 2E. That's it. So what you observe is they will repel each other. This is going to repel this, this is going to repel this. Due to repulsive force at one point, the whole kinetic energy of this will come to a point, let's say at this distance R0 from the gold nucleus, where the alpha particle will completely come to rest momentarily, and then again it will rebound back. These distance, the minimum distance between the nucleus, between the minimum distance up to which an alpha particle coming along a straight line can reach to the nucleus is called the distance of closest approach. The minimum distance up to which an alpha particle alpha particle can reach while traveling along a straight line, traveling along a straight can reach uh, can reach near the gold nucleus while traveling along a straight line, while traveling along a straight line traveling along a straight line while traveling along a straight line uh, joining the center of the two parts, and joining the center of the two is called this joining their centers is called closest approach. Distance of is called distance of closest approach. Is called distance of closest approach. Now we can find an expression for this. Very easy. It is based on conservation of total mechanical energy. So you can see at this point, what will happen here is whole kinetic energy at this point will become equal to what? The potential energy of this. And if you remember, potential energy of two charge system is K, Q1, Q2 by R. In this case, what is Q1? Q1 is charge on this, which is 2E. In this case, what is Q2? Charge is ZE. Therefore, at O, at O, what will happen? Kinetic energy will be equal to potential energy. So let's see, because sum of them is 0. So you need to know this expression. So half mv square is equal to kze into E by R naught. So this is the main fundamental equation regarding this. Correct? Now let us see the next part of the question. The second part says, how will it be affected? For an alpha particle, if kinetic energy of particle is doubled. If kinetic energy of the particle is doubled, okay. If the kinetic energy is doubled, let's say, so instead of calling this half mv square, I'll call this E. So E equal to half mv square is equal to k ze square by R. Now given if E is double, you can see E is R naught. E is inversely proportional to R naught. Okay, E is inversely proportional to R naught. So if E is doubled, E1 is the initial one, which is K ze square by E square by R naught, initial state. Second condition is what? E2. E2 would be what? Kze square by some value, let's say R dash, R naught dash. Okay, this is final condition. So we need to find what will happen to R naught if E2 is doubled. Given what? Given E2 equal to double of E1. So take the ratio. So E2 by E1 will give me, always whenever they come ask you make questions like this, you should solve by comparing. So E2 by E1. E2 is kze square by R naught dash divided by kze square by R naught. As you can see, everything get cancelled. This goes here, R naught by R naught dash. So implies E2 by E1 is equal to R naught by R naught dash. Now what is given? E2 equal to E1. E2 is given as 2E1. Plug it. So 2E1 is equal to R naught by R naught dash. So I can see my E1 cancel. So 2 is equal to R naught by R naught dash. R naught is the new distance, new closest approach. So R naught dash should be now R naught by 2. So it gives what? Half. So it will get by how much? Half. If kinetic energy is doubled. If E equals to half mv square is doubled, some basic is doubled, what will happen? The closest approach will get distance of closest approach will get reduced by half. R naught will get reduced by half. That's it. Let's proceed to the next one. The next question. A point source. This is from ray optics. So for ray optics, a point source in air is kept 24 centimeter concave spherical glass. Okay. Concave spherical glass surface and the radius of curvature is 60 centimeter. So let's see. Let us draw concave. So this is the concave surface. This is a concave surface. This is the principal axis of the concave surface. A point source is kept 24 centimeter concave, 24 centimeters. So here is our point source. Let's say it is placed 24 centimeter in front of a concave spherical surface. So this from here to here, this is 24, and radius of curvature is 60. So this is 24. I think it's too near. I have drawn. So let's say from here to here, this is 24, and from here to here, this would be, let's say, 60. Then the length we can see is quite comparable like that. So any ray is a concave. First, what you should do, you should draw the normal. So this is the normal here. Now, any ray which will be originating from the point object here, point source here, you see, in the rarer medium, it will be moving away from the normal. But in the denser medium, what it will do? It will try to move towards the normal. So somewhere like this, it will try to move towards the normal. So that if I extend this, so somewhere here should be the, I think I should draw it more properly. Once again, this is the green one, and here is the red one, the 24 centimeter one. You can see move away from the normal. So it would be somewhere here, somewhere at the back. It would be, the image will be, final image should be produced. So this is given 24, this is given 24 centimeter, this is given 60 centimeter. We need to find where is V, how far is V. As is, this is N1, this is N2, N2 is glass, so glass is 3/2. If you remember that in our course, in class 12 course, there is this relation we have done, refraction of spherical surface. So refraction of spherical surface, the relation is minus N1 by U plus N2 by V equal to N2 minus N1 minus N1 by U plus N2 by V equal to N2 minus N1 by R. So from here, any combination you can derive it. Any configuration on this question, whatever come on this category, you should be able to solve it from here. So let's see how to solve this one. So what is provided? So distances, listen to this, distances measured with the direction of light is taken as positive, and the distances measured in the direction opposite to the direction of light is considered negative. So in this case, U will be, you can see U, this is the direction of light, so U would be minus 24 centimeter. And what is R? R is also, again, I'm measuring from here, this is our origin. So from here we are measuring, again it should be minus 60 centimeter. Minus 60 centimeter. Then refractive index of air, which is given as, you see, air to glass is N1 equal to 1 and glass or 2 is 3/2. What do you need to determine? V you need to determine. So put it minus N1 by U plus N2 by V equal to N2 minus N1 by R. So N1 is how much? 1. U is how much? Minus 24. Plus N2 is how much? 3/2. V is equal to, again, 3/2 minus 1 by R is how much? Minus 60. Let's solve this. So you can see this gives me 1 by minus 2 into 60. That's good. So let's solve it. So then I'll go to next page. So minus 1 by 24 plus 3 by 2v is equal to uh, minus 2 into 60. So from here what we can do, we can take 2 common out. So if I take 2 common out from here, this will be minus 1 by 12 plus 3 by v is equal to minus 60. So let us bring this 3 by v is equal to minus 1 by 60 plus 1 by 12. I think in between them, this is v by the way, sorry, this is v. This is v. Now 60 and 12, what is the LCM? So 2, 3, 30, 2, 6 are 12, 2, 15, 2, 3. So 5 3s are 15 and 3, sorry, 3 5s are 15, 3 1s are 3. So 2 2s are 4, 3 4s are 12, 12 and 5, 60. 60 is the LCM. Okay. So then this gives me 1 and that gives me minus 1 plus 5. So that gives me 4 by 60. Let me see. Lots of concentration is needed here. So 2 2s are 4, 2 3s are 6, 30. So that gives me V is coming as, there should be 1 minus. Just a minute. Okay, I did the mistake here. It is a minus there. So minus minus it will become plus. There's already minus there. So this one will become plus. So this is plus. So this one should be, how did I get this? Why it should be minus? Because see, the ray diagram is saying this should be backward. So that's why. That created me doubt here. So it should be, I'll do it from here once again. So this one should be 3 by V is equal to, now again, it should be 60 LCM. So that gives me 1 and minus 5. So that gives me 5 minus, this is minus 6 by 60 there. I get here minus 1 by 10. So V is equal to minus 30 centimeter. Let's go back to our diagram. So where is minus 30 centimeter? Here. This is minus 30 centimeter. So how much is this? Then what? Find the nature of the image from the any distance from the point source. If you stop here, how much is the marks? Is 3 marks. You are going to get 2.5 marks. So last part is this. This is our O. You need to find OI. How much is O? O, you need to find, this is C, sorry. This is C. This is C. This is O. So how much is O and I? You need to find the O and I. You can see. So distance between mod, you can take this OI, distance between O and I mod. It should be how much? Doesn't matter. So 24, 30 minus 24, 6. That gives me 6 centimeter. Done. So that is your answer. This would be your half mark. This is how we generally awarded marks in the board. So we should solve it. Even if you, these relations doing correctly also very important. Let us see the next question. So this is not there in this time, this in the course. So I'm not doing that. Let us come to the question number 7. See how easy these questions, and these questions on optical fiber keep repeating. So you must do this question thoroughly. Don't go without knowing on optical fiber. So what is optical fiber? So optical fiber works on the principle of total internal reflection. Let us revise you. What is total internal reflection? So TIR is this, that when you see this is a interface separating two medium. When a ray of light in the rare denser medium is incident at an angle greater than the critical angle. So here is the critical angle ray. Then what will happen? This is IC. This is incident at an angle greater than IC. Greater than IC. What will happen? The reflected ray will get completely, the refracted ray will get completely reflected within the denser medium. This is called total internal reflection. So I'm saying once again, when the incident ray in the denser medium is incident at an angle greater than the critical angle of the denser medium, the refracted ray will get completely reflected within the denser medium. This phenomenon is called total internal reflection. Which Where do you use this? You use it in case of optical fiber. Now, what is an optical fiber? Optical fiber uses the same principle. This diagram of optical fiber is very important. You see there is a core, and there is a central core which is made of higher refractive index N2, and there is another outer refractive index N1. This is called cladding. The outer refractive index is called cladding, CLADDING, cladding. This is called N1. So N2 has to be greater than N1. So when a ray of light is incident at this, what will happen? It will undergo total internal reflection from here. It will come out from the other side. This is the case of optical fiber. So explain with the help of suitable diagram the phenomenon on which optical fiber works. Optical fiber works with the principle of total internal reflection. Just explain it. Draw with this diagram. Total explain. Explain total internal reflection. Finish. Done. Mention any two uses of optical fiber. So optical fibers so optical fibers are used in case of medical uses. First of all, communication purpose. Okay, communication, high speed, bandwidth, internet. It is working on this communication purpose. It is used in medical photography. Medical photography inside human bodies. Medical photography using inside human body. It is used in there. Then they are used in many cases as sensors, light sensors. So these are different uses of optical fiber. Got it? So in this case, what you need to do, just explain total internal reflection, which is this one, and then give the uses. Done. This may be awarded 2 marks, and this may be awarded 1 mark, or this may be awarded 1.5 mark, and this may be awarded 1.5 mark. Got it? So next, let us see a parallel beam of light of wavelength 600 nanometer. Question number 8 is incident normally in a slit of width 0.2 millimeter. The resulting diffraction pattern is observed on a screen 1 meter away. Find the distance of the first minima, second maxima from the central maxima. Okay, let us see this. So here it is saying that the parallel beam of light of wavelength 600 nanometer. Parallel beam of light of wavelength 600. So let us draw it a little bit to see. So this is the parallel beam of light. That means a plane wave front. This is front of a diffraction. It is going through here. Then what happens? It produces a central maxima there. So how does central maxima look like? Central maxima is going to look like this. This is a central maxima. So from here we can draw one line. The diagram is very wrong. Let me draw a line first. Yeah. So central maxima will be somewhere here. So this is the central maxima. This is the central maxima. Okay. What do you need to do? Is given that first find the distance of the first minima. This is the first minima. Then there are like this. This is first maxima. Then there would be this. This is the second maxima, and so on. I will draw the graph here once again properly. On a side one, this is intensity distribution curve. Intensity distribution curve for this type of is very important. So diffraction intensity curve and interference differential curve, you should always don't go without knowing this. So this is the intensity distribution curve of diffraction. This is first minima, first minima. This is first maxima. This is first maxima, first maxima. This is second minima. This is second maxima, and so on. Same here. This is also on the other side. Let us keep it on the left hand side, one direction only. We'll do. So now the question says a parallel beam of light of wavelength 600 nanometer is incident normal in a slit of width 0.2 millimeter. This distance is 0.2 millimeter. Okay. If the resulting diffraction pattern is obtained on a screen 1 meter away, this is 1 meter. Good. Okay. Wavelength, how much? 600 nanometer. The resulting diffraction pattern observed on a screen 1 meter away, find the distance of the first minima. So distance of the first minima is this one, We'll call this x from here. As you can see, if I draw a line from here, if I can draw, this is actually theta. This is theta. Okay. So fringe width, as we know, fringe width beta of the central maxima is 2 lambda d by d. But we only need x. So x is actually nothing but half of this beta, that is lambda d by d. Lambda is how much? Lambda is 600. So 600 into 10 to the power minus 600 to the power minus 9 into d is 1. Small d is 0.2 millimeter. 0.2 into 10 to the power minus 3. If I solve, 600 into 10 to the power minus 9 into 10 to the power 3 divided by 0.2. I'll take the 10 also here. So 3, 4, 5 minus 5, and this gives me 6 by 2. You should always do it like this. Then you should not be any mistake there. 2, this 100. So 2 minus 9. And this power is minus 10, the power is 3 and 1 4 plus 4. So 4 by 6. 6, that gives me minus 3. So this gives me 3 into 10 to the power minus 3, or that gives me 3 millimeter. So the position, first question done. Position of first minima is how much? Position of first minima is 3 millimeter. Done. Position of first minima is 3 millimeter. Let us see the position of second maxima from the central maxima. Second maxima. So to look at the second maxima, we need to look at this. Let me take this to the new page. Here I'm going to revise you one thing, which is, let us draw this first. If you remember, the position of minimas is given as you can see, position of minimas is given as coming from this path difference. D sine theta n is equivalent to theta is equal to d theta n is equal to n lambda. Whenever theta n, angular width, is equal to n lambda by d, we are going to get a minima. And when theta n similarly will be equal to 2n plus 1 lambda by 2d, this is going to be maxima. So if you can see, this is the first minima. So first minima, put n equals to 1, it is lambda by d. This is first maxima. So for maxima, n should be equal to 0. So this is lambda by 2d. This one should be how much? This one is second minima. So second minima means 2. So that should be 2 lambda by d. This one is what? This one I'm not writing here. This is the second maxima. So second maxima n equal to 1. Put n equals to 1 in here. So 2 plus 1, 3 lambda by 2d. 3 lambda by 2d. So we should get here 3 lambda by Yeah, 3 lambda by 2d. Let's see. So now what will be our solution? Let's see. No, I'm doing one mistake here. Wait a minute. Little mistake here. It is this, not that. It should be 2n plus 1 by 2 lambda by d. Yeah, this is the series. This is the series. So this one should be, so for this one it should be n equals to n equals to 1 in this case. So 2, this one should be 3 lambda. Yeah, 3 lambda by 2d. This one should be 5 lambda by 2d. This is fine. Sorry, this is fine. This should be 5 lambda by, please remember, you need to keep in mind this one. This is odd series, this is even series. 5 lambda by 2d. So then theta is coming as, so theta for second maxima is 5 lambda by 2d. But again, just like we did it for the central first minima, we can also do it for second maxima. This is our second maxima. How far is it from here? Let's say this is at a distance of x dash. This is that theta. So tan theta in this case will be equivalent to theta, as angle is small, is x dash by d. So x dash by d, and theta is how much? This. So we can write this as x dash by d. So x dash must be equal to how much? 5 lambda d by 2d. So we can write this as 5 by 2 into lambda d by d. But wait, lambda d by d to we determined just now. How much is it? It is 3 millimeters. See, lambda d by d, 3 millimeters. So we can put it there. So it should be 5 into 3 into 10 to the power minus 3 by 2. So that gives me, so 3 1.5. So 5 into 1.5 into 10 to the power minus 3, or 5 5s are 25 and 2 5s are 6 7, 7.5 millimeter. So that is the position of the secondary maxima in this question. This is a good question. You should know this kind of question for high order problem. So this is, again, if you solve this, 3 marks done. Okay, let us see the odd question. Let us see. So thin equivalent equiconvex lines of radius curvature R made of material refractive index mu1 is kept coaxially in contact with an equiconcave lens. Equiconcave lens means something like this. This is a radius of curvature R of material of refractive index convex. So this is convex. This is concave, equiconcave. They are placed like this. Correct? Now what is in contact with equiconcave lens of same radius of curvature? Both the cases R is same, and refractive index and to find the ratio of their power. So we know from Lensmaker's formula. Don't go without knowing Lensmaker's formula. Don't go. So what is the Lensmaker's formula? 1 by f is equal to n2 minus n2 by n1 minus 1 by 1 by r1 minus 1 by r2. So you can see now for the first lens, I'll call this L1, we'll call this L2. So for L1, you can see focal length for convex lens, f1 will be, f would be positive. By the way, this relation can also written like this: p is equal to n2 by n1 minus 1 by r1 minus 1 by r2. So for L1, which is a convex lens, so for convex lens, R1, this side is R1, that side is left one. So R1 is equal to plus R and R2 is equal to minus R. So power 1, power of convex, power 1 will be equal to glass. So 3 by 2 minus 1, and this will give me 1 by R minus 1 by R. So that gives me 3 minus 2 is how much? 1 by 2. So it gives me 1 by 2 into 2 by r. So that gives me 2 to cancel 1 by r. So P1 is plus 1 by r. Similarly, what do you think P2 would be? So P2 will become now both of their, okay, refractive index is not same. Sorry. Refractive is mu1, and that one material of refractive index mu1 is kept coaxial in contact with equivalent. Okay, refractive index is not same. I cannot use this. Sorry. My mistake. I didn't notice that. It is different. So, yes. So, let's see. So, P1, we will write like this once again. N1 minus 1 by R1 minus 1 by minus R, not R1. If both are should be R and R minus 1 by minus R. So I should get here N1 minus 1, and this should be 2 by R. That's it. This is P1. Similarly, what will be P2? So L2, for L2, which is equiconcave lens, R1 will be negative R, and R2 will be positive R. So I should get here P2 should give me here refractive index is, in this case refractive index will give me same N2 minus 1, and then minus 1 by R minus 1 by R. So that gives me N2 minus 1 by 2 minus 2 by R. So this is P2. Let us take the ratio of their powers. First question. So P1 by P2, this is 1. So P1 by P2 would be what? Take the ratio. This is N1 minus 1 equal to N1 minus 1, and then 2 by R divided by minus N2 minus 1, 2 by R. So you can see everything get cancelled. I'm left here with N1 minus 1 by minus. Why don't I distribute the minus inside? If I distributed 1 minus N2. So this is the answer. P1 by P2 should be equal to N1 minus 1 by 1 minus N2. Done. This is the first question done. Second, power of the combination. So power of the combination is, equivalent power is P1 plus P2. So power 1 is how much? Power 1 is, this is the power 1. So N1 minus 1 by 2 by R, and this would be plus, no, not plus, it would be minus N2 minus 1, 2 by R. Shall we distribute this? So if I distribute this, we should get N2 N1 by R minus 2 by R minus 2 N2 by R minus plus 2 by R. As you can see, these two get cancelled. So what is left here? I get here 2 by R common. This one should be 2 N1 minus N2 by R. That's it. This is the answer to the second one. Finish. Let's see. Now, the photoelectrons. The photoelectrons are emitted from metal surface. Question number 9. Are emitted from metal surface. The photoelectrons are emitted from metal surface when illuminated with UV light of wavelength 339. It is again from the photoelectric equation. The minimum amount of energy required to emit the electrons from the surface is 3.5 10 to minus 19 joule. This one kind of question you can always expect in every board exam, CBSE board year, every year. So what is given? Let's see. You need to find energy of the incident radiation. What is given? Given is lambda. Incident lambda is 330 nanometer. That is 330 into 10 to the power minus 9 meter. Minimum amount of energy required. How much? Minimum amount of energy required to emit the electrons is given. From the surface is this. That is also provided. So we will see this. Work function is given to you. This is work function. 3.5 into 10 to the power minus 19 joules. Questions regarding this can be very lengthy. So you try to understand the question and properly. If you see while solving question on this kind, it is getting too lengthy, stop it. You maybe not, because they will not give any question which will get too lengthy or too troublesome. They will not kill you so much of time, but they will try to confuse you. So in this case, what you should do, if it is taking too much complicated, too much you got trapped, you are doing wrong. Stop it, rethink it, and see if you can solve it by your they will ask you straightforward questions, not very tricky here. Now, maybe tricky, but not lengthy. So let's see. So you need to find the energy of the incident photon. E is equal to, first question done, very easy, hc by lambda. From where did I get this? H nu, but nu is how much? C by lambda. So h c by lambda. H is how much? Planck's constant 6.6 into 10 to the power minus 34, and that is 3 into 10 to the power 8. Lambda is how much? 330 nano. 330 into 10 to the power minus 9. If you solve this, you should get it. So it will take some time. I'm not doing it. Please solve it. You should get directly. The answer will be definitely in joule. Now for the second one. Now the kinetic energy of the photoelectron. From Einstein photoelectric equation, what do I know? H nu is equal to phi naught plus kinetic energy. We need to find kinetic energy. So kinetic energy must be equals to how much? H nu minus phi 0. H nu is how much? H nu is the incident energy, whatever we get it here. Let's see if we can solve this roughly. So whatever energy you get it from here, it will take some time. I'm not solving. So whatever energy you get it here, plug it the value here minus this thing, 3.5 into 10 to the power minus 19. If you solve it, you should get the value of energy. Remember, this thing should be going here. You should get the answer in joule. That is question number 9. Again, 3 mark. Done. Direct formula based question. LED is not here this time, so I'm not discussing question number 10. Let us see question number 11. Monochrome light is incident on a source to separating two medium. The frequency of light after refraction remains unaffected, but its wavelength changes. Why? This is just straightforward explanation based question. Let's see. So monochromatic light means single color light. As you can see, the first question's answer is this. You see, frequency. Monochromatic light is incident on a surface separating two medium. The frequency of light after refraction remains unaffected, but its wavelength changes. Why? Because refractive index n is inversely proportional to lambda. N is equal to, relative refractive index n is equal to lambda 1 by lambda 2. Lambda 1 is medium 1, lambda 2 is in the medium 2. Wavelength in medium, lambda 1 is the wavelength in medium 1, lambda 2 is the wavelength in medium 2. So refractive is inversely proportional to lambda. Okay, so that's why we can see n equal lambda by lambda 2. So you can easily solve this. How? Let's see. So the answer to this is that frequency is the characteristic of the light source. It cannot going to change. It will not change. Frequency depends on the source of light. On the source of light and not any other, not the source of light. But wavelength depends on the refractive index of the light, the refractive index of the medium. Hence, hence, hence wavelength changes, lambda changes, not new. The frequency of electron radiation is 1 10 to the 11 hertz. Identify the radiation. So we know that 10 to the 11. So somewhere here you can see this is 10 to the 14, this is 10 to the power 15. 14, 15. From here if I go by 2 distance, that is 12. So 11 is here, 10 to the power 11. So this must be infrared. IR, because this is red, this is violet, this is UV, this is infrared. So this must be infrared. Mention 2 uses. Where do you use it? So incident radiation is infrared. What are 2 uses? What are uses? Uses in remote. Use in remote. Again, these also used in communication. Using communications. Communications. So rather we can use it in greenhouse effect. Greenhouse effect use. Then infrared lamps. Detectors, IR detectors. So many, it has so many applications. So with this, I will close the stream for today. The remaining is only 2-3 questions. Maybe in my next session, I will finish this and carry on with the next one. This point onward, the questions are quite easy, only not very difficult as well. So it should not take much time. Yeah, these are MCQs here. The hard questions are there. Remaining you can try on your own. They are not very difficult from this point onward. If any question, any doubt, please text me. I will definitely solve that. Hard questions I have solved from this paper. So in my next session, I'll start with the next question. Next, I'll start with the some other paper. Okay, thank you.